Hello again and welcome back. I'm pretty excited today because this lecture begins the study of the differential calculus, or derivatives. The last few lectures we looked at limits and continuity, and today we're going to use those ideas to define the concept of the derivative of a function. And this is based on that tangent line problem I did way back in lecture 1. So let me briefly review that problem for you. Remember that we looked at the parabola f of x equals x squared, and we selected the point 2, 4 on the parabola and asked what is the equation of the tangent line at that point. Basically, we're asking what is the slope of the curve at that point. And remember how we did it. We picked another point q of coordinates x, x squared, and we formed the difference quotient, change in y over change in x, and that simplified down to x plus 2 as long as x was not equal to. And then we made the following observations. As q approaches p, the secant line pq approaches the tangent line at p, and that's equivalent to saying that x gets closer and closer to 2, and then we said the limit as x approaches 2 of x squared minus 4 over x minus 2 equals 4. Good. Well, let me put some notation in front of you now. The function we dealt with there was f of x equals x squared. The point was c equals 2. That was where we wanted to find the tangent line. And f of c, the function value there, was 4. So that previous limit that we just looked at can be written as follows. Slope equals the limit as x approaches c. Remember, c is 2. X approaches c. The numerator is f of x minus f of c, and the denominator is x minus c. It's the difference in the y values over the difference in the x values. Keep that in mind throughout. That is how we define slope. And lo and behold, this notation that I just showed you, limit x approaches c, f of x minus f of c over x minus c, that is the definition of the slope of the tangent line to a curve at the point c. Great. So now we have the definition of slope to a curve. Here's a picture of what I just talked about. Notice that we have the point c, f of c, and we want the slope at that point. The neighboring point is x, f of x, and then we formed the difference quotient, change in y's over change in x's, and that gave us our definition. Now, there's an alternate notation that you'll see in many, many calculus books that is often very useful to use in applications. Let me explain how this works. The point x is near the point 2 in that example we just did. So think of it as being 2 plus delta x, where delta x is some small number. So we're going to say that our nearby point is 2 plus a little bit delta x. And that means that x minus 2, if you subtract 2 from both sides, is delta x. Think of delta x as being the difference between x and 2. And then our formula, x squared minus 4 over x minus 2, becomes, well, replace x with 2 plus delta x. So it's 2 plus delta x squared minus 4 divided by, well, x minus 2 is just delta x. And in general, for an arbitrary function, you have the slope equals the limit of f of c plus delta x. That's 2 plus delta x in our example, minus f of c divided by delta x. And you take this limit as delta x approaches 0. That's equivalent to saying that x approaches 2, because x minus 2 equals delta x. So that's the alternate definition of the slope of a curve. Hey, don't panic here. It's the same concept. There's no difference here except in the notation. Here's the picture. Our point was c f of c, and the neighboring point is c plus delta x, comma, f of c plus delta x. Notice on the x-axis you have the point c, and then the neighboring point is c plus delta x. As delta x goes to 0, that point motors down towards c. Good. So a study tip here. First of all, that notation delta x usually denotes in mathematics a small change in x, Some books use h for this small change, but I prefer to use delta x because it kind of reminds us of the change function, change in x. Those two definitions of slope are equivalent. They mean the same thing, and you should keep in mind that picture, and that will remind you that in both cases, all we're doing is computing the slope of a secant line and then taking the limit. And by the way, as we'll see a little bit later, that limit, of course, it might not exist, it might not have a tangent line, but it also might be infinity or negative infinity. And in those cases, if that limit is infinity or negative infinity, we say that the graph has a vertical tangent at the point. And again, we'll see an example of that later. But for the time being, keep in mind that our definition of slope has two versions that are actually the same thing. Let's do an example, a pretty simple example. Let's find the slope of the graph of f of x equals 2x minus 3 at the point, say, 2, 1, which is on the graph. Well, what's the obvious answer here? If you want to know the slope of that function, what's the answer? Well, it's a straight line. 2x minus 3 is a straight line. Its slope is 2, because that's the coefficient of x. So I know what the answer is supposed to be here. But now I just want to test ourselves on using the definition. So here we go. Here are the characters. The point that we're approaching is 2. So c will be 2, and f of 2 is 1. That's f of c. So we use our definition. It's the limit as delta x goes to 0, f of 2 plus delta x minus f of 2, all divided by delta x. Now watch what happens. What's f of 2 plus delta x? Well, you take the function. The rule is f of x is 2x minus 3. So every time you see an x, you replace it with 2 plus delta x. So you get, in the numerator, 2 times 2 plus delta x minus 3, and then finally minus f of 2, which is minus 1. And that's all divided by delta x. And now simplify the numerator. This, by the way, this will always happen in these problems. Your numerator will simplify, and then a nice cancellation will occur. So I'm going to do the numerator. It's 2 times 2 is 4, and then it's minus 3 minus 1, so that goes away. The constant goes away, and I'm just left with 2 times delta x in the numerator. I have delta x in the denominator. The limit is as delta x goes to 0, so I can cancel that common term delta x, and I get the limit of 2 over 1, which is 2, as expected. Great. Okay, so I think we're now comfortable with the definition of tangent line, how to compute the slope of a tangent line using that definition. It requires a limit calculation. It's non-trivial. Well, lo and behold here, that limit definition that I just gave you is precisely the limit of the so-called derivative of a function. I kind of slipped that in here, didn't I? This is the definition of derivative. It's nothing more than the following limit. Limit as delta x approaches 0 of the following quotient. In the numerator, it's f of x plus delta x minus f of x, and the denominator is delta x. Think of this as being your quotient of difference of y values divided by difference of x values. And the most common notation for derivative, or one of the most common notations, is f prime of x. So f of x is the function, and then f prime is its derivative. And we say that a function is differentiable at an x if this limit exists. Okay? So our goal in the next few lectures is to learn how to calculate the derivative of a function, and we'll develop some rules in a little while that will make it pretty easy. And then to use this derivative to describe the behavior of graphs. What do graphs look like? And in particular, we'll be able to do lots of applied problems, optimization problems, finding maximum and minimum values of functions. Now, I'm the first to admit that it's difficult to use this definition, but sometimes it's necessary to use it. But rest assured that in the coming lectures, we'll develop lots of rules that will let us evaluate derivatives without having to use this definition. But sometimes we have to use it. The history of derivatives, the development of the derivative is a long history. I mean, we're talking about the development of calculus. And some of the names that I've mentioned earlier, Fermat and Descartes back in the 1600s worked with derivatives. They didn't have a full grasp of the concept of limit, but they were able to use the limit definition and compute derivatives in their engineering applications. The Dutch mathematician and physicist Christian Huygens did a lot of work with derivatives, as did Isaac Barrow, who was Isaac Newton's professor. In fact, the story is that when Isaac Barrow identified Newton as being so talented, he gave up his office to Isaac Newton at Cambridge. And remember that Newton and Leibniz independently kind of put all calculus together and are often thought of as being the inventors of calculus, but they were building on earlier results. The derivative is going to play a major role in this course as we go along. Has many, many notations. It's kind of sad that this happens in mathematics, that a single concept can be written many different ways. It's sort of unfortunate, but we have to be aware of all these different notations because you might read a different book, you might pick up a physics book, and the notation looks different to you. Here's some of the notations you might see in other calculus books or in physics and engineering books. F prime of x or dy dx. I like that notation because that reminds me that the numerator is the change in y and the denominator is the change in x. Y prime is a very common notation. I like that notation because it's not too hard to write down, just y prime. Another notation is d dx of your function, which you put in brackets. And then if you take a course in differential equations, which usually follows a calculus sequence, you'll often see the notation capital D of y. That means the derivative of y. Also be aware that they use different letters for x and for the function f. It's very common to have the variable be t for time, and the function might be the position of a particle or the velocity of a particle. We'll see some of those examples later in this course. Okay, so where are we? We have our definition of derivative, an unpleasant definition, I'm the first to admit it. Let's get our hands dirty. Let's do a fairly complicated calculation to show how to use that definition. The advantage of this calculation is I think you'll enjoy it. You'll be able to follow it, I think. But then when we're finished with it, we're going to interpret our results in terms of slopes of tangents. Because remember, this derivative is nothing more than the slope of the tangent line. So let's find the derivative of the function x cubed. F of x equals x cubed, a nice little polynomial. Remember, it's an odd function. It's symmetric about the origin. Let's find its derivative. Well, the derivative would be that limit, f of x plus delta x minus f of x all divided by delta x, and you take the limit as delta x goes to 0. In all of these problems, you cannot just plug in 0 for delta x, because look at the denominator. It would be 0. So you have to do some manipulations. Let's see how to manipulate this one. The numerator will be f of x plus delta x, which means you take x plus delta x and you cube it. And then you subtract f of x, so minus x cubed, and all divided by delta x. Cool. How can we simplify this? Well, we've got something cubed. We're going to have to multiply that out. Ouch. That's pre-calculus algebra. It's another sort of unpleasant algebra skill we have to bring to our calculus course. So here's the multiplied version of that cube. It's x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. And then at the end you have the minus x cubed, all divided by delta x. So sorry about that pre-calculus. Please practice that step so that you're comfortable with multiplying out a cube of a sum. Well, now look at the numerator. Magic happens. The x cubes cancel each other. The one on the far left with the one on the far right. Wow. So I'm left now with a whole lot of terms, all which have delta x in them. So factor out that delta x. And what are you left with in parentheses after you factor out the delta x? Well, you have the 3x squared, and then you have 3x times delta x, because originally it was delta x squared. I factored out one of them, so I'm left with another one. And then the third term would be delta x all squared, and in the bottom I have my delta x still. And now the miracle occurs. You can cancel the common factor of delta x. You're always looking for this in these computations, that cancellation. And you're left with a new limit problem. Here it is, 3x squared, 3x delta x squared, and you ask yourself, what happens as delta x goes to 0? Well, wow, the second and third terms go to 0, you're left with just 3x squared. And so, what do we have? Our limit at the end is 3x squared. Here's some notation for you. The derivative of x cubed is 3x squared. You should be proud of yourself. You just calculated a derivative. This is maybe your first derivative. The derivative of x cubed, of the function x cubed, is 3x squared. Now, what does that mean? Let's interpret that. What's the slope of the function, of the graph of the function x cubed at 0? Well, plug it into the derivative. It would be 0. 3 times 0 squared. What's the slope at 1? It would be 3. What's the slope at minus 2? It's 12. Plug in minus 2. Here's a graph of x cubed. What's the slope at 1? The slope is 3. The curve is rising there, isn't it? It has a positive slope. How about at minus 2? The slope is 12 there. It's really going up fast. The slope is 12. It's getting very, very steep there. And notice the symmetry here. Notice that the slope of this curve is always positive except at the origin. At 0, as we saw earlier, the slope is 0. Now, by the way, to recap this problem, it was pretty difficult to use that definition to calculate the derivative because we needed some pre-calculus skills. We had to expand a cube and we had to do some cancellations of the delta x. Later on, we'll have some nice formulas to simplify our life. Let's look at another example of a derivative calculation and see if we can use the definition again to determine whether or not a function has a derivative. Let's look at the absolute value of x minus 2. This is similar to the absolute value of x, except it's been shifted 2 units to the right. Do you think it's going to have a derivative there at 2? Do you think it's going to have a tangent line there? What does your intuition say? Well, here's what my intuition says. That it's going to have a slope of minus 1 to the left and a slope of 1 to the right. But at 2, things are not so pleasant. There seems to be a sharp corner there. It's not clear how you would have a tangent line there because it's not really, it would sort of wiggle there, wouldn't it? It's got sort of a sharp point. But let's not think geometrically. Let's go back and do it analytically. Let's take our function and ask the following question. Is it differentiable at 2? Of course it's continuous there, but is it differentiable there? So I'm going to use one of the definitions of derivative. F prime at 2, which is f prime at c, that's our definition, is the limit of the change in the y values divided by the change in the x values. So it'll be f of x minus f of c over x minus c, and we take that limit as x approaches c. So let's fill in the characters. What's the function? Absolute value x minus 2. What's f of c? That's f of 2, so that's 0. And the denominator is x minus 2. And we ask the limit as x approaches 2. That's nothing more than the absolute value of x minus 2 divided by x minus 2. Well, what about this limit? Do you recognize that as a diving board function? I hope so. Look, as we approach 2 from the right, the function wants to be 1 because the numerator is positive there and it's equal to the denominator. But as I approach from the left, it's minus 1. So that limit does not exist. So it does not have a derivative at 2. Geometrically, the function had a sharp corner there. Let me say it this way. If you have a derivative at a point, you will be smooth there. You'll be smooth. You won't have sharp corners and things. Having a derivative means you have a tangent line. So it's got to be a smooth curve for that tangent line to sit next to the curve and just kind of kiss it once. By the way, you might have noticed in this problem, I used one of the alternative definitions of derivative. Both of those definitions would work in this calculation. Let me show you another example. I remember I mentioned earlier about vertical tangents. Let's look at another problem that's kind of interesting and I think pretty important. The function x to the 1/3 is continuous everywhere. It's defined for all values of x. This is the cube root function. The cube root of 8 is 2. The cube root of 0 is 0. The cube root of minus 8 is minus 2. You can take the cube root of any real number. Okay, is it differentiable at the origin, at 0? Of course it's continuous. It's continuous everywhere. Does it have a derivative at 0? Well, something interesting is going to happen when we use the definition. Here we go. Let me remind you what the definition is. F prime of c at any point c is the limit as x approaches c of the difference in the y values, f of x minus f of c, divided by the difference in the x values, x minus c. Well, let's plug in the names of our characters. The function's x to the 1/3, f of 0 is 0, and the bottom is x minus 0. And that simplifies. Oh boy, here we need some work in simplifying exponents. It's x to the 1/3 divided by x. Remember that you subtract exponents. That's the same as 1 over x to the 2/3. Some pre-calculus. So we're asking the following question. What's the limit as x approaches 0 of 1 over x to the 2/3? Well, as x approaches 0, x to the 2/3, the cube root squared, also approaches 0, and 1 over a small number is a big number, and that limit is infinity. So we say here that x to the 1/3 has a vertical tangent at x equals 0. It's not differentiable at 0. Let's be clear about that. The limit does not exist, but it has a unique behavior. It's actually equal to infinity, but it does not exist. Not differentiable there, but it has a vertical tangent. Here's a picture of x to the 1/3. Now you might notice something here that's kind of interesting. X to the 1/3, we observed that at 0, the curve has a vertical tangent. In a sense, it's instantaneously vertical as I cross the origin. Now remember what x cubed looked like? X cubed is the inverse of x to the 1/3. It's kind of like a flip. For x cubed, the derivative at the origin was 0. And here, it's a vertical tangent. It kind of got flipped up. Isn't that cool? Yeah. Later on, we'll talk about the relationship between the derivative of a function and the derivative of its inverse. Here you sort of see that happening right now. Now, there is a relationship between differentiability and continuity. The theorem goes like this. If a function is differentiable at a point, then it is always going to be continuous at that point. But the converse is not true necessarily. Continuity does not necessarily imply differentiability. And we've seen that in those previous examples, that absolute value function was continuous at 2, but not differentiable at 2. Here's an example I like to do in my classes. And I do this with a graphing utility, so I invite you to go along with the lecture and use your graphing utility to do the following experiment. Put in the two functions x squared plus 1 and absolute value of x plus 1 into your calculator and zoom in to the graph near the point 0, 1. Here's a picture of those two functions before I've zoomed in very far. One of them is a parabola with a y-intercept of 1, and the other is the absolute value function moved up 1 unit. So they intersect at 0, 1. Now zoom in a few times. What's going to happen as you zoom in? Well, I hope you sort of say the following. The absolute value function will continue to have a sharp corner no matter how close you get to it. And it's not going to be differentiable there, is it? It's not going to have a derivative at the point 0, 1, because it has a sharp corner. The parabola x squared, you can sort of see that the tangent line there is horizontal, isn't it? It's horizontal. And so as you zoom in, that parabola will look more and more horizontal. So do that experiment at your leisure, and you can verify what I just said. Now, in the old days, calculus books didn't have many pictures. But nowadays, with graphing calculators, the exercises and layouts of books has changed enormously. And there are a lot of problems like the following problem that I'd like to look at. It's a problem that requires some thinking rather than calculations. Here's how it goes. I'm going to give you the graph of a function. You give me back what you think the graph of its derivative would look like. Isn't that curious? I'm not going to tell you what the function is necessarily. I'm just going to give you its graph. And you come back with its derivative. So let's try it. Here's a function. Now, let's suppose we don't know its equation, but you would probably guess that this function is maybe the straight line y equals x, f of x equals x. So that's a line. What's its derivative going to look like? Well, let's think about this. The derivative is the slope. What's the slope of this straight line everywhere? Well, it's approximately 1, because this looks like the line f of x equals x. So the derivative probably looks like this, the graph of y equals 1. That's the derivative. Isn't that neat? Let's do it backwards problem. Now I'll give you the graph of the derivative. You come back to me with the original function. Suppose I said the derivative, this time I'll give you the specific value. Suppose the derivative is minus 2. So the derivative is minus 2, the horizontal line minus 2. What's the original function look like? Well, remember, the derivative is the slope, and it's always minus 2. Well, can you think of somebody who has a slope of minus 2? Well, a straight line of slope minus 2. So any straight line with slope minus 2 would work. Here I've drawn a couple of straight lines of slope minus 2. There are an infinite number of answers here, aren't there? There are a lot of straight lines with slope minus 2. They have different y-intercepts. By the way, you just solved the differential equation. I gave you the derivative. You gave back the function. That's called solving a differential equation. Not a real hard one, but you just did it. Well, I hope you've enjoyed our first approach to derivatives. It was a generalization of the slope concept. Please memorize that definition of derivative. Just memorize it. It's really important. I admit that it's difficult to calculate, as we saw with the example x cubed. We saw some examples of functions that don't have derivatives at certain points. And now in the next few lectures, we're going to develop formulas for finding derivatives. This will make life a lot easier. But as I said earlier, sometimes we're going to have to go back and use that definition. So I look forward to seeing you next time when we develop our formulas. Thank you very much.